Okay, so last time, we looked at graphs plus some conditions on the graphs. And we associated to graphs numbers, the real numbers. And we also introduced something which are numbers modulo integers modulo a prime power. And these functions from graphs to real numbers or graphs to Z mod QZ satisfied lots of combinatorial properties. Okay, so the next topic is the diagonal sequence. So this is quite a big subject of research. It's very elementary, but there are still many deep things to be discovered. So we take f, a polynomial, in d variables of degree d. Sorry, homogeneous. And we define delta nf to be a coefficient of x1 xd to the power n in f to the n. And so we get a sequence of integers. And so if you're wondering what this means for n equals 0, it's just 1. It's the coefficient of 1 in 1, which is 1. So a fact which I'll be more precise about later, but for now it is enough to know that this sequence satisfies a polynomial recurrence, like I mentioned in the first lecture. Polynomial. So we'll come back to this later. And there are many famous examples. Typically, these diagonal sequences enumerate something. If you want to count, paths from one point to another, loops in some lattice or some with certain movements that you're allowed to do, then these diagonal sequences are a very good way of counting. Of solving such combinatorial problems. But the examples we've seen already include sequences that we saw in lecture 1. So these were Apery, the Apery sequence, etc. of lecture 1. Okay, and so we talked a little bit about counting points over finite fields. I mentioned briefly last time that these were related. So recall that I denoted FQ to be the number of points X xd in FQ to the d, such that f of x is 0. That's an integer. And the theorem I mentioned briefly last time, and I don't know who it is, it's certainly ax, but I think it's before ax, less than or equal to ax, is that if q is just a single prime, then the point counts of fp is congruent to -1 to the d minus 1 delta p minus 1 of f mod p. And this has some fantastic consequences. And just to prove my point that there's so much to do with these elementary ideas that is not necessarily known. With my co-author Eric Panzer, we wondered, can we get FQ from the diagonal? And it turns out this was not known. So it's still not known because we haven't written a paper yet. But this is in progress. Maybe January. Eric Panzer, who's in Oxford, that this generalizes to all prime powers. Let me just give two examples. If you want to count points over fp squared, then this is congruent to 2 delta p squared minus 1 delta p minus 1 squared mod p squared. Fp cubed etc. There's an infinite sequence of formulae. So this looks like this is just the Pascal's triangle. It's not. It's more complicated. The next term is more complicated. In any case, what I wanted to say is there's a slogan, which is the diagonal determines point counts over FQ mod Q. And so there's an interesting interplay here with the fact that the diagonal satisfies a recurrence relation. So if you only know the first few terms, you know everything. And the fact that you get these point counts for all these different infinitely many primes. So there's some very tight control constraints here. And it's not really been explored at all. So a corollary of this, these equations aren't obviously consistent. If you scale f by a number, then this doesn't change, but this does change. So it looks strange. But the reason it's consistent is because the diagonal in general satisfies many interesting congruences. So this is a whole field of research. There are many congruences of many types. It's a whole subject, but you're lucky that you have an expert here. The first one of the first references is due to Masha and Anton Menit. There's recent work of Masha and Fritz Beukers going much further than this. In fact, Masha is the expert on many of the things I will say today. Okay, so this diagonal is very important, and it tells us all about these arithmetic questions of finite fields. That's one fewer thing to have to think about. We just need to study the diagonal. So let's look at the diagonal in the case of graphs. So this is very interesting. So let's take G, a finite connected graph, such that the number of edges is twice the number of loops. Then I remind you that we had the graph polynomial, which is the sum over spanning trees. And then we took one monomial given by the product of edges not in each spanning tree. And by assumption, we can look at psi g squared, which is homogeneous of degree equal to the number of variables by this assumption. So the degree is twice hd, and the number of variables is eg. So this implies that. And so we can define the diagonal sequence of a graph. Delta naught psi squared g, delta 1 psi squared g, dot, 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 dot. And this is the diagonal sequence. So this is very, very recent work. I'll give references in a minute. So let's just do a very simple example. G is this graph, our favorite example. 1, 2, 3, 4. So the graph polynomial was alpha 1, alpha 3, it's alpha 1, alpha 4, it's alpha 2, alpha 3, it's alpha 2. And so you can check that the diagonal sequence in this case is 1, 4, 36, 400, 49, 4,900. And in fact, delta n is 2n choose n squared. It's a closed formula. So let's look at delta 1. So delta 1 of G equals coefficient, so this is 4. So number 4 is the coefficient of alpha 1, alpha 2, alpha 3, alpha 4 squared in psi g squared. Okay, so let's... Sorry, Paul?
So we define this because for polynomial we defined delta 0 to be to the power of 0, so delta 1 to the power of 1.
It's a mistake, thank you. Thank you very much. Yeah, because it's 2n, but I'm doing delta 1. So there's a 1 here, but I square here. Thank you. Okay, so so how do we do this? Well, we multiply this with itself, and we want to make this. So let's write out psi g, we have alpha 1, alpha 3, alpha 1, alpha 4, alpha 2, alpha 3, plus alpha 2, alpha 4, plus alpha 3, alpha 4. I could write it again and pair up, but I leave you to do that in your heads. So if I multiply it with itself, I'm going to take a monomial here and another one and multiply them together. So I can get alpha 1, the way to get this is I can multiply alpha 1, 3 with alpha 2, 4. Or I can multiply, or the other way around, or I can multiply alpha 1, 4 with alpha 2, 3. And so that gives me the two ways of doing this, either alpha 1, 3 in one factor and alpha 2, 4 in the second one, or the other way around. That gives 2, and 2 plus 2 is 4. But let's think what that means in terms of graph. The psi is, these terms are spanned by spanning trees. So what this is counting, it's saying that G can be written as a union of the spanning tree 2, 4, with 1, 3, or it can also be written as the union of 2, 3, and 1, 4. So what this delta 1 is doing, it's counting how many possible ways we can cover the graph G with two disjoint spanning trees. And so that turns out to be a very interesting combinatorial invariant, which is kind of old, but it's kind of new. So this is what Panzer and Yates called the Martin invariant. And this is just to illustrate this idea of the diagonal is a machine for generating lots of very interesting mathematics with very little effort. So this is in a very recent paper of Panzer and Yates from 24 on the archive. So they call this the Martin invariant. It's related to something that Martin did many years ago. So delta 1 of G equals the number of ways to write G equals T1 disjoint union T2 union, disjoint union of two spanning trees. And so these guys prove the following theorem, which is in the paper. So if G has vertices of degree less than or equal to 4, so all the vertices have degree less than 4, then 1 delta 1 of G only depends on G hat, the 4 regular completion. So we discussed that last time, but I can, in this graph, what you do is you pick an extra vertex infinity and you join it to the other vertices in such a way that every vertex has degree 4. And therefore, delta 1 of G is twice what's called the Martin invariant, or what they call the Martin invariant of the completion G hat. So let me tell you what this is. And it has some amazing properties. First definition. Suppose G hat is 4 regular. So for any 4 regular graph, you define n invariant of this as 1. And now to do it in general, what you do is you pick any vertex and you want to compute the Martin invariant of your graph so that your graph looks like this. Has a vertex V which is 4 regular. So it has some edges coming off it. And what you can do is you want to delete this vertex to get a smaller graph and do an induction. But you need to stay in the world of 4 regular graphs, and so the only way to do this is to reconnect these so there's too many edges here. Is to reconnect these vertices in some way, so you can do it like this. Or you can do it like this. Or you can do it like this. And so you've expressed the Martin invariant of a graph with a certain number of vertices in terms of Martin invariants of graphs with fewer vertices. So this is extraordinary, and it's some very famous relation in knot theory and graph theory called the STU relation. So it's a very, very important relation. It occurs in many, many different areas. So this says that if you look at this diagonal sequence, just the very first interesting number in the diagonal sequence already gives you a very interesting invariant of graphs. And what they do in their paper is they explain how all the higher diagonals, the higher elements in the diagonal sequence are also can be related to something. And in fact, maybe quickly I'll just say delta ng is related to higher Martin invariants. I mean, they call them Martin invariants, but they really invented them, these authors. And what you do is you look at the usual, the same definition, but of a graph which is not 4 regular, but much higher degree of regularity. So Gn replaces each edge E with many copies of the same edge. That's the rough idea. I think it's G hat. Anyway. Okay, so this diagonal gives you lots of new combinatorial objects which are being studied. So the next question is, how do we get back to periods and the things I discussed in the first lecture? So how to relate all this to integrals and periods? Because all this is very combinatorial, and we don't see the connection with, we don't see any real numbers. Okay, so the first step is to go back to this diagonal and interpret it as an integral. So this is very well known. So delta nf by definition was the coefficient of x1 xd to the n in f xd to the n. And that's the same thing as the residue of f of x to the power n of dx over x1 dxd over xd. I mean, more simply, it's just that it's the constant term in this power, and the constant term in this expression is the same thing as the residue of this expression. Perhaps I shouldn't change notations. And a residue we can write as an integral. So this is going to bring us gradually closer to integration. So this residue equals, by Cauchy's theorem, 1 over 2 pi I to the d integral over gamma, where gamma is a product of small circles around 0. I don't know if you, otherwise you can write the notation like this if you prefer. I don't know if this is standard notation or not. Okay, so we've taken this diagonal, which is very sort of combinatorial. It's counting something, but we've managed to write it as an integral. So the next thing I want to do is to sort of imagine what happens when if n is negative. It doesn't make sense, but if n were negative, what would happen is that these x1 up to xd would be on the numerator, and the f would be in the denominator. And if we did that, we'd get a Mellin transform. Mellin transforms, or these are algebraic Mellin transforms. So consider the function s maps to I of s, where we're going to do what I said. So here we're going to take sigma some domain. It doesn't really matter for now. I'm going to choose some later, some domain of integration. And we're going to assume that this converges. It might not converge. If f is going to have, this is going to have some singularity, some pole somewhere. They better not meet sigma. So let's just assume that this actually converges. And you can be very precise, make this very precise, but I don't want to. So let's assume it converges for the real part of S bigger than or equal to 0. So this should remind you of the sorts of things we looked at when we looked at these proofs of irrationality of zeta 2 and zeta 3 and so forth. We had things just like this, but S was an integer. So that's what we're going to do. We're going to look at what are called the Mellin moments. And that gives us a new sequence. I0, I1, I2. And this gives us an infinite sequence, but now of real numbers. So we have two sequences. We had the diagonal sequence, which is just some integers. And now we have some sequence of real numbers, which are some interesting periods, some interesting, possibly transcendental numbers. So how are these two related? So there's a theorem, I'm going to be slightly vague, which is this sequence, the new sequence eta, satisfies a polynomial recurrence. So under the right assumptions, which are mild, but there's no point being too precise. So for example, if f is positive on the interior of the domain of integration, that's one such assumption, maybe some other technical assumptions, but not very strong. In that case, it turns out that this function I of S is uniquely determined by these Mellin moments. By the IN, for n an integer. So if you know these integer values, you can uniquely interpolate them to get the value of this function for all S. And so the interesting thing is that we can also look at the diagonal sequence, but write it backwards. And the diagonal sequence is a sequence to the same recursion. Is a solution the same recursion. In other words, we have one recursion whose solution in the positive n is these Mellin moments, and has a solution in the negative direction, which is the diagonal. So what that means is something quite concrete. So what we can do, in other words, we can splice together the diagonal delta 3, but do it backwards. And splice it with the Manin moments. And now we get a sequence which is infinite in both directions. So these are our integers, and these are typically real numbers. So un is in if n is bigger than or equal to 0, and delta 1 minus n if n is strictly less than 0. N minus r. N is minus 1, I'm going to get 1 minus 1, thank you, yeah. Minus 1 minus n. Yes, I agree. So this is how the diagonal and these transcendental integrals talk to each other. Then, then un satisfy a single recurrence which I remind you from lecture 1 what a polynomial recursion is. It's something like this. Where Pin is a polynomial in n associated to and so a conjecture, the conjecture will seem strange to you because you think it might be implied by the theorem. But the conjecture is that under the right hypotheses, so I think this is a provable conjecture. In other words, a conjecture in progress, whatever that means. Then the diagonal, if you know the diagonal sequence, then you know the recurrence. And if you know the recurrence, then you can presumably know all these Mellin moments. And so you need a little bit of more information to do that. And some things can go slightly wrong. You could find that the diagonals satisfy this could sort of factorize, and it could satisfy a smaller smaller recurrence relation. There's some little subtleties here, but morally speaking, and in all the examples, this is true. So the diagonal determines the recurrence completely. And hence, again with some small assumptions, once you know the recurrence, you can determine all these numbers. And that part we can do. And all the in via what are called Apery limits. So I'll explain that in a minute. So it's saying that if you know, and in all the examples we have, if you know the diagonal, just some integers, you can reconstruct all these integrals, and you can therefore reconstruct the entire Mellin function.
The question about zeros of this polynomials. That's where we can.
No. So what the problem is that if you have a sequence, the recurrence it satisfies is not unique. Right? There is the smallest possible recurrence, but it's like saying, a zero of a polynomial. The polynomial is not unique. It's an ideal generated by the polynomial that's unique. So I could have this could be too big. So in other words, this might not be irreducible. It might break into two smaller recurrences, And I could be very unlucky that it breaks into two recurrences, and IS is solution to one of them, and delta is solution to the other one. So if I know delta, it gives me one of the recurrences, but the IS is the solution to the one. So that could be extremely unfortunate. Well, we think that doesn't happen. It's like saying if you have a function annihilated by a differential operator, well, it's also annihilated by a bigger differential operator. And this is the problem. This may be somehow a product of two differential operators. It might not be minimal. So if it's minimal, this is trivial. But we don't know why this should be minimal in some sense. But it always seems to be. And I don't know, to be honest, if that's a very difficult, a very deep thing, or if we just make the right hypothesis, we can solve that. I mean, with some hypotheses, we know exactly what the asymptotics of the solutions are, and I think that might be able to solve this problem. But philosophically, it's kind of extraordinary. It says that you do this combinatorics on getting some integers, and from it you can reconstruct something transcendental.
The thickness of i's on the right depends on the cycle of integration, sigma.
Yes.
One of the left does not.
You're right. So the right hypothesis. So what happens in the examples I'll show is that, and all the Apery examples, were that sigma was chosen. I said this in the first lecture, that xn vanishes along the boundary of sigma. So in this case, it'll be like a simplex or a hypercube. And this condition means that this integral is going to go to zero very, very fast. It will turn out to be the minimal solution of this recurrence relation. So if there's a unique minimal solution, which is normally the case, then you can reconstruct it uniquely from the... If you know the recurrence, you can reconstruct the unique minimal solution. And so under those hypotheses, the I can be uniquely constructed from that. But in general, there's a vector space of solutions, and the general machine, there are many Apery limits, and they will generate the vector space of solutions. It's just in this case, we have a particular choice of the solution that goes to zero fastest. So let's look at this in the case of graphs. So we have G with the usual hypotheses. The number of edges is twice the number of loops. And to make my integrals converge, we need this subdivergence-free hypothesis. And then this gives rise to something which should be called the Mellin-Feynman integral. Or maybe Feynman-Mellin, I don't know. So IGS will be the integral from 0 to infinity to the number of edges minus 1. Product of all the alpha E over psi squared alpha E graph polynomial to the power S d alpha 1 d alpha ng minus 1 over psi squared. And I need to set everything. I need to set alpha ng equals 1 in this. Right? I can do a projective version, but it's simpler just to set one variable to 1. And this doesn't depend on which variable I set equal to 1. And so this is what we call Mellin-Feynman integrals. It converges for, under this assumption, it converges for all real s bigger than or equal to 0. And it's a much more rich object, than the Feynman residue, because of course we can retrieve the residue just by setting s equals to 0. So this is kind of the philosophy of all this, these lectures, that there's this rich theory of periods, but I claim that to really understand it, one should look at these Mellin transforms, which give families of periods and recurrences and all this extra structure. So we saw that with the irrationality proofs, and we're seeing it now with in the context of graphs. Okay, so let me finish with one detailed example. So let's take G, the wheel with 3 spokes, which was residue was 6 times zeta of 3. And so the recurrence is this. You might not want to write this down, but 2 times 2n plus 1, just to make things very concrete. So it's a recurrence of order 3. Sorry, of order 2. Oh, sorry, this is wrong. N plus 2 here. Oh, sorry. This is n plus 2 here. Okay, I've written it the opposite way that I did before, but it's correct. So it's a second order recurrence, and these polynomials have degree 5, I think. So the funny thing is that I wrote this down in 2014. I was trying to think about irrationality of zeta of 3, and I thought, aha, let's try to use these examples from physics to see if we can get new approximations to zeta of 3 and other zeta values. So I computed this in 2014, and I gave some lectures on it. I gave one lecture on it, and I completely forgot about it. It turns out the approximations are not as good as Apery's ones. And then Eric Panzer was computing diagonal sequences of graphs, and he noticed that they satisfied recurrence relations. And I said to him, okay, send me the recurrence relation. And it looked completely different, but I did a change of variables, and in 30 seconds later, I had found exactly the same recurrence that I'd calculated 10 years before. And so it was a very happy coincidence, because I wrote back to him and said, we understand exactly where your recurrences come from. Actually, his recurrences came from the Martin invariants, so it was quite surprising. And that's how our collaboration started. So it shows that, things come back in unexpected ways. So what's the sequence of Mellin moments? It's the residue 6 times zeta of 3, (6 over 60 zeta of 3 minus 7 over 360, 6 over 900 zeta of 3 minus 173 over 129,600, etc. And so this equation has 2 fundamental solutions. Over Q. So it always has a vector space. It's of degree 2, so it has a vector space of dimension 2 of rational solutions. Why? Because I can just put the initial values 0, 1 and 1, 0. So the first solution, we can just take the coefficients of 6 zeta 3, 1, 160 over 900. The next one is 47, 400, 400. And then the B solutions are the constant terms, 0, minus 7,360, minus 173. So you can pick any old basis of solutions to this. So that's this, etc. But over the real numbers, over R, there is a unique minimal solution, which is this one. So it's a particular real linear combination of these rational solutions, which asymptotically goes to 0 fastest. So it's slightly subtle that there's the rational solutions and the real solutions behave differently, and that's the whole point of the Apery limit. So what is the Apery limit? So if you know this recurrence, you can write down a basis of solutions over Q. And then you can reconstruct the number zeta of 3 from these, okay? So what you see is we know that Ig of n equals an 6 zeta of 3 plus bn, and this is asymptotically lambda to the n for some small lambda. It's exponential decay. Like we saw in the first lecture. So how do we compute lambda? Well, it's very easy. You take, so lambda is the smallest root of the characteristic polynomial. Of star. So how do we get the characteristic polynomial? Well, we just look at the highest power in n. So as n is very, very big, this is n to the 5. And then when n is very big, this term dominates here. 65 n to the 4, 2 times 2n. And when n is very big, it's 4n times 4n, 4n. And so we get a polynomial which is 1024 lambda squared, which I've done it correctly. It's 4 times 4 times 4 gives 1024. Then minus 260 lambda, which I think is 65 times 4, and then plus 1. And this turns out to be 256 lambda minus 1, I think, 4 lambda minus 1. And so the smallest root is lambda equals 1 over 256. So this thing tends to 0 stupendously fast. And it implies that we can capture the residue Ig 6 zeta 3 can be obtained as the limit Ig equals the limit as n goes to infinity of minus bn over an. I think that's right. Yeah, and so what is bn over an tends to 0, it converges like 1 over 64 to the n, which is the ratio of these two roots. So again, this tends to 0 incredibly, this tends to 60 to 3 incredibly fast. And this is important because in physics we don't know how to calculate these residues. It's the million-dollar question. People spend their lifetimes trying to compute these integrals, and we need to know them for the Hadron Collider. If we could do this in general, it would give an incredibly efficient way to calculate Feynman amplitudes, Feynman integrals, in a way that converges extraordinarily fast. Okay, so that's called an Apery limit. I've reached the end of my time. but we've sort of come full circle and gone back to the sort of Apery type irrationality questions we started with. By the way, this is not good enough to get the irrationality of zeta 3 because the denominators are bad, unfortunately. So here's a sort of picture of some of the things I've tried to talk about. We have Mellin-Feynman integrals up here, and these are related to polynomial recurrences. So Mellin or Feynman, or Mellin-Feynman. From the polynomial recurrences, we saw how they were related to diagonal sequences. And the diagonal sequences were related to lots of arithmetic in number theory, like point counts over finite fields. But in the case of graphs, they also gave lots of interesting combinatorial invariants for free, like the Martin invariant. But there's several others which I didn't mention. And from the polynomial recurrences, I've tried to illustrate how we can take an Apery limit and we get interesting periods. And we studied two particular examples. We studied Feynman residues in high energy physics. And we also looked at the sorts of things you get in irrationality proofs in the first lecture. So for zeta values, etc. So here, so what this theory is doing, these Mellin transforms are somehow providing a completely elementary connection between very different things, for arithmetic over here, counting and combinatorics, and transcendental numbers over here. So I've tried to share some of the things that I find that I love, and that are elementary but deep. And thanks for paying attention.